wish I could increase the font size. We'll survive. Thanks for having me here. I guess the genesis of this talk was a dinner at NeurIPS. And I think I was on a roll, as sometimes happens at dinner. And specifically, maybe I've done a lot of work in the area of distribution shift. I think there's within the branches of the kind of different maybe schools of thought on how to approach this technically, a bunch of different lines of literature, some on I'll get into it, but maybe some on distribution shift as causal learning in disguise, some on let's play the deep learning playbook and make this into an empirical problem, some on I don't know, kind of let's do best in the worst case over some class of things that could happen kind of approach, and produced thousands of papers, produced thousands of methods, and none of them are useful. And I say this as like a card carrying, like someone who's spent a lot of my academic career working on various lines here. So I'm not throwing stones at someone else's house. I'm sitting in the house and throwing stones at myself and others. But I just wanted to maybe like give a little bit of a meta talk of I sit on two sides now, and I'll maybe talk about that. I'm an academic still. I'm also operating a company that is maybe the fastest growing vertical AI company, fast growing healthcare technology AI company right now, where we're involved in the problem of automating a lot of the drafting of medical documentation. So have all kinds of distribution shift problems, and nothing that I've worked on or that anyone else has worked on, to my knowledge, has been useful to me. So I think it was maybe a reflective talk to step back on how we got here, what we've done, and maybe, I don't know, where we're going, or what is the future of this line of inquiry. So I guess if this talk had a title, which I probably didn't send a title, but it would be maybe something like Shifts WTF. So I think if we flash back to like 2014, we were sitting in a world where, for one, machine learning was primarily an academic discipline, and not an industrial discipline. So I think what it meant to do machine learning in industry was either to be actually an academic hanging out like in a little pocket of industry that was allowed to exist, like Microsoft Research, or it meant that you were working on advertisements. I think this was one area where like machine learning was quite successful, and there's probably something going on in quant finance that maybe Martin knows more about than I do, and in general, probably nobody who was actually working on it was allowed to talk about it. So I think we had a perception within academia that like most of the problems that actually captured our imagination as academics were, insofar as we were application-oriented folks, were not advertisements. So we had a sense of machine learning will go on to do all these great things, and they're things that it's not actually doing in the world right now. There was not an industrial discipline around it. So it was largely, a lot of like machine learning for healthcare, which was my home turf, was a lot of dreaming from the standpoint of sitting in a computer science department of what we might be able to do, procuring data sets, and then playing around in like little offline sandboxes and imagining how the sort of prediction problem we've set up might relate to some technology that one day could exist and be deployed, but isn't currently being deployed. And from this standpoint, started to, some of us, just focus on how do we get better models? How do we work on more interesting data sets? How do we work on bigger data sets? What are new prediction problems we should work on? But also a lot of us started tackling like what's fundamentally missing, like what's missing from this setup such that people aren't using this stuff. And I think so if you look at like what was the paradigm of what we were doing, was largely collect a data set, call something the inputs, call something we want to predict the outputs, or the targets, usually execute like a random train test split, train on one set, evaluate on the other. There was a conviction at the time, I think, that academia was concerned with many different flavors of ML, but that everything that was even sort of making it into application, for the most part, supervised machine learning, That's a perspective that I think has, not aged so well. And so we were training models, we were getting asked some predictive performance. We're like, well, why aren't people using this? And so maybe this broad program emerges of like the real world ML agenda, the sort of papers that start off with machine learning has blah 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 blah, but in the real world, and like the words real world would be italicized to let people know you really mean it. The author usually is someone who has never written a line of production code in their life, and what came under like that umbrella, like under that cone of study. A lot of different things. There's all kinds of desiderata that matter in the real world that are not accounted for here. Concerns about, usually if you're a business, the reason why you're using any kind of system is because it is doing something. And the doing part was sort of maybe underappreciated. So that there was a lot of gaps on how do we get from predictions to decisions. There was a lot of concerns about fairness. This line of research emerged because we were thinking, well, there's ethical import to things that we build in the real world, systems that we deploy. How are these represented in our problem formulation? So we want to stick that in there. There was a whole line of interpretability research. I'm going to lay off that one. Don't want to poke that bear. And an important one was this sort of robustness agenda, the shifts agenda. I've trained the model, and any conclusion that I have about predictive performance is on the basis of the fact that I've evaluated it on some data set that is randomly partitioned from the same underlying population as my trained data. And it was no mean feat. For a long time, we weren't able to do that. Like even within like the kind of IID setup, we were not able to get models that were very accurate on the holdout data. So it's a big thing that we got to this world where we were starting to do very well in a lot of these problems. But then there was this, but is that really enough? How I'm going to go out in the real world, and I want to deploy this model in a different location at a different point in time. What licenses me to do that? Why should I be confident? Like why? And so you have a lot of these arguments that are swirling around the time. People are saying, I need to interpret the model. Unclear interpretability was like a catch-all for some magic sauce that like will then make you feel good about it. Then you have someone like Jan LeCun saying, why do I need to interpret the model if the model is accurate? Then you have someone else come back and say, what does accurate mean? What does it even mean to be accurate? Because to be accurate in the real world is to be accurate on this population from which you don't have any samples. So, and that was maybe, a line that I was attracted to say like, well, when can we, and this maybe is like gets like the fundamental problem that animates, I think, like all, at least from my perspective, the way I parse it, I think the way like a lot of social scientists want to see this is like, this is the fundamental problem of causality, right? It's like, when can I take data, you could have the narrow view of causality of like, it's about treatment effects, but the broader view of like, when can I take data sampled from one population and draw a conclusion about some different population? And so in the case of distribution shift, it wasn't necessarily like the hypothetical population in which I intervene in some way, but it was like this new population from which I have unlabeled data that I'm collecting in the wild, and I want to say something about my accuracy on it, or how, if at all, I should adapt my classifier. And what's changed today? A lot of things have changed today, like how we go about constructing AI systems has changed, like how we go about getting functions that perform desired behaviors has changed. It's not always about tuning weights. Sometimes it's about tuning prompts. Sometimes it's about using people's intuition to construct these orchestrated workflows. As concerns training data, that's actually used, the distribution shift problems, like what even is the distribution from which models are created anymore? Nobody knows. But when you get down into like a target application, well, we do have data often from like the application of interest. And the fact that the underlying model was trained on who knows what, maybe doesn't matter so much. That's just part of the definition of a hypothesis class. So anyway, back into the program of distribution shift. Like, well, what are the fundamental problems? A number of challenges emerge. One is like, can I detect that there's been some shift in the population? Can I detect shift? Another is accuracy estimation emerges as a problem. Can I say when I should expect that, or be worried that there might be a dip in accuracy of my system in the new deployment setting? can I estimate some particular parameter of interest on the new distribution? So in my case, I spent a lot of time working on various flavors of the label shift problem. So often estimation problem of interest, like can I estimate the new label distribution that I'm encountering in the world based on the fact that I have a model trained on some source distribution, and now I have unlabeled data from the new deployment context. And maybe the most aspirational was this question of like, can I correct my classifier on the fly? Can I find a way to just adapt my model? And so a bunch of lines of work emerge. In general, like there's a very basic sense in which the problems we care about are impossible. You're like, you care about problem X, I give you data from unrelated problem Y. What can you do? So like faced with that kind of conundrum of the thing we seek to do is just obviously fundamentally impossible from the outset, the community kind of forks. And some of us say, well, absent any assumption about what links some source distribution P and some target distribution Q, what is it that they have in common? I can't say anything about performance by classifier. I don't have any labels on whatever I come up with. There's the possible world where the label's the opposite of what I want it to be, and God is just mischievous, and so what? We're screwed. So the kind of the NEETs want to see this as a causal problem. We want to say, well, what is the identifying assumption that we could make that will say under this identifying assumption, the collection of data that I have, the things that I observe, the set of variables that I observe on the source distribution and target distribution are sufficient to identify the parameters I care about. Sufficient for me to be able to detect shift, to estimate accuracy, to adapt my classifier. And then the dance becomes something like, what are the sets of assumptions that we could work with, and how plausible are they, and what are the corresponding algorithms that would exploit those assumptions to give us what we want? I can get into some of the work that I've done on that front. There's also other people who, oh, my landlord is calling me, decline. That come up with this other thing of saying we want to do something like produce a classifier that does as good as possible in the worst case over distributions that are near to my distribution, but like I've related via some divergence measure. I think this doesn't actually give us something that's useful for any kind of real world task that we care about, because any sufficiently distant distribution to be a thing we would actually encounter in the real world would give us like just completely vacuous results. It just comes out like saying something like make your model smoothish. And there's a lot of people out there who say like, well, we didn't get here by proving things. And that's not maybe popular to say in this room. We got here by trying stuff. So let's do the same thing. Let's try stuff. And the problem is like, well, try stuff as evaluated how? And it used to be, well, try stuff as evaluated on the test set. And the move here is to say, well, let's try stuff as evaluated on shifts. And this is where things get a little bit weird, because, I'll get into that, but what do you mean by shifts? Like what is the population of shifts? And I think this is something that like is like a very deep kind of question. That's like easy to like kind of just say, I don't want to think about it, let's just write a paper. But I think this ultimately is like the Achilles heel of like almost all the work in this line, and why nothing's been useful is that is there such a thing as like what shifts are like? Not clear. So maybe just go in just in a little bit of resolution. I got a little bit obsessed with it seemed to me like my attitude at the time was like, oh, the only route forward, the only way to say anything even remotely like philosophically coherent is to be able to make some kind of assumption and then make some kind of leap that it uses that assumption to derive some like useful machinery. It's like first thing I did in this kind of line of work was I was just like agonizing over a puzzle. Turned out to be like a problem that's been out there for a while, but I just didn't know at the time. I was just worried about like, hey, people use machine learning often for like quantification problems. I want to do sentiment analysis. I want to know how many people are saying positive things about some entity on Twitter or something. Like people do this all the time, and it seemed like there was just something fundamentally broken about that problem. You train the model, on some collection of data. Now you deploy it in the world, and the whole fundamental problem is, well, the sentiment is changing. And so given that sentiment is changing, whatever it is that I think about the performance of the classifier, which was based on the idea that nothing is changing, is invalidated. So like, what gives me the right to say anything about what is the sentiment, now in the new period? Or working in medicine, motivation would be something like incidence or like of a disease. Flu, I have a classifier that recognizes based on symptoms or based on chest x-rays, predicts how likely someone is to have the flu. And it does a good job on the test set. It, gives me, say, I don't know, calibrated estimates. If I take the average over the population of like people have the flu, I get an estimate for, what fraction of the population has a flu. But now I go in the real world and it doesn't say 1% of people have the flu, which is what it said on the test set. In the real world, it's telling me 5% of the people have the flu. So now all I know is that I can't trust my classifier, but how many people really have the flu? So I kind of went deep down this rabbit hole, and it turns out, well, what assumption can we make? And the natural assumption was something like, well, the relative proportion of the labels could change, but P of X given Y, the class conditional distributions doesn't change. Yeah, what's up? You have a question? You never have a question.
Yeah. So, I mean,
Shock.
To phrase the problem in a general sense, but maybe the way is just to say, we are not going to have a general theory, but for this particular application.
That's what I'm talking about. That's what I'm talking about. So I'm saying, like, I'm saying it's impossible in general. So let's make a particular assumption. Particular assumption that I'm focusing on here is really narrow. Is I just want to be just a little bit wider than ID. I just want to say not anything can change. The class conditional distributions, P of X given Y, is not allowed to change. The only thing that's allowed to change is P of Y.
I'm not saying make an assumption. I'm saying fix your target application. I only want to care about predicting a certain disease. Now, see what assumptions are relevant to predicting a disease. It may not be good for predicting whether an animal is a cat or a dog.
Maybe. I think we'll get into orbit. So, first of all, I mean, there's the question of, either way, you're getting to assumptions. You're maybe not talking about the particular assumption I'm working on here, but you're saying, I want to fix an application and come up with an assumption. Maybe I was working a little bit, I was fixing an application. I was saying I got this chest x-ray problem, and I want to estimate prevalence of disease. That's my case. So I do thought experiment. I say, what's the relevant assumption? I come up with my label shift assumption. And then, kind of say, well, what would be a valid procedure here? What would be an efficient procedure for now estimating the label distribution in the wild? How would I update my classifier in light of that information? What would be the correction to apply? And it turns out, and I'm also doing this maybe in the deep learning era. So like the move that was exciting was to say, oh, I can make this some high level assumption. And the trick that we kind of fell into was this world where, hey, if I could train a good source classifier, like just on the original distribution, I could train a good input-output classifier. So it was like good in some not so crazy sense. Just maybe I knew what its confusion matrix was in the source distribution or something like that. It was reasonably accurate. I don't need it to be have some wild properties that if I had this, and I have some identifying assumption, that I could come up with some set of routines where it's like I could sort of take that source classifier and it's sort of done all of the representation learning work, so I don't have to worry about the input-output relation, and take the source classifier together with some post-hoc gymnastics that incorporate this assumption in order to produce the estimates that I want for whatever parameter I care about on the test set, or that could maybe just adapt that classifier to now go from being a good classifier in the source distribution to being a good classifier in the target distribution by incorporating the unlabeled data that I have from the target. So I got obsessed with this, worked on the label shift problem, figured out that label shift wasn't just the case of, we could go further, not just when the relative proportion of previously seen labels have changed. We could also go out and look at situations where there was a new label that was never previously before seen during training. So this is related to like if you had one previously seen label and now you have two labels at test time, this would be the problem called, basically it's isomorphic to what's been called like PU learning, positive and unlabeled learning, we figured out we can go further than that. We could figure out identification scenarios where under the label shift assumption, we could deal with multiple previously seen classes and the relative proportion is changing and a new label arrives. And be able to recognize, not just recognize, but also produce a classifier. So like we have a K-way classifier, the relative proportion of the K classes changes and the new one arrives, and we're able to produce a K+1 way classifier. And this is exciting. And we could kind of go down this path of like enumerating like identification conditions and saying like, how far can we get? And coming up with some get the proofs, say, suppose I can do a good job of classification on the source distribution and say I can prove something nice about what I could do with that to get good classification performance on the test distribution. Problem here, of course, is I've never encountered a pure label shift problem in the wild. So, and that is like maybe the most basic assumption I could work with. It would feel like I could do something with it, but it's just there's always something else changing. It's not the case that you go out and like the relative dogs versus cats are changing, but all the individual breeds of dog have like increased in prevalence at the exact same rate, and all the cameras have stayed the same, and everybody's clothes look identical. It's like it's never the case. So I've never found a case where like I can apply this machinery and have a classifier that's like automatically adapting itself on the fly and now producing better estimates and also like updating the input output behavior without like a human in the loop on the fly. To my knowledge, it's never existed. The literature has sort of run away with this kind of thing, but I think it's a playbook we've seen in causality too, of you could probably like unfortunately like tiny the number of like cases of confidently identified causal effect actually determined based on observational data in the wild, but the number of like exotic playbooks that enumerate, under assumptions A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, like you would be able to, if you believed all these things, surprisingly determine, a causal effect given a certain amount of data, whatever. And then, everything shifts from it's like identification puzzle plus estimation puzzle, but the reality is nobody uses it, right? So we find ourselves in this world of like, feeling good about ourselves philosophically because we're able to say something rigorous like, hey, under this assumption, and I even have a story about why that assumption might be well motivated, I would be able to show that, but I don't actually ever get to make that assumption or apply it. On the other world, you have people saying, we're going to do the empirical distribution shift work. We're going to look at, say, what are shifts like? And I say, well, how are we going to come up with a shift? And we're academics. We don't have access to problems in the world. So we say, okay, let's create shifty data sets. So for every data set that previously existed, now we have the shifty version. So you don't have just MNIST, but you have MNIST M, and you have CFAR-C, and ImageNet I, and I don't know, LibreSpeech L, and you have this sort of like I don't know what's the word, infestation, metastasis of kind of like artificial data sets that are like with like constructed shifts so that we can try out methods. And then you have a bunch of people coming up with algorithms, and here nobody's said anything about when it should work versus when it shouldn't work. And we already know a priori that it's easy to like in the absence of an assumption, it's easy to construct the settings where it doesn't work. So people say, but let's look at the data sets that we have. And you have a relatively small number of these. And people go to town and they start coming up with things. We have domain adversarial learning. We have tricks involving pseudo-labeling. We have a lot of every kind of, all the sorts of things that like occur as like the tinkery things you could do as a deep learning practitioner. What if I jiggle this? What if I look at that? What if I take the label from this and then you just kind of write out, just use your imagination to say, here's a procedure, and then let me just look and see how I did on the shift data sets. And so there's something like deeply problematic about this whole enterprise, right? And among other things, it's not clear like that there is a what shifts are like. We're also, even insofar as there was some notion of what shifts are like, the effective sample size here would be the number of data sets that you had seen, not the number of samples that you had seen. And so then, there's folks like, I don't know, is Peng Wei around? I think he was listed. anyway, like Pongwei and Shiori and a bunch of folks at Stanford go find a bunch of different applied folks in different departments and get together a kind of compendium of data sets. They call it wilds. And it's just like, here's a bunch of data sets from a bunch of different places. And we'll say there's like a bunch of different time periods, or there's a source and there's a target distribution. And of course, you take everything that everyone had previously done and you apply it on the wilds data set. And the kind of conclusion you get out is nothing works, or nothing works consistently. So we're in this, we're in this problem that we're sort of in a things work when they work, and they don't work when they don't work. And what you lack is any kind of principle to say which scenario you're in. So the takeaway from wilds might have been like, hey, we've got a deep problem here, like unclear if we're making progress or have a route to make progress. But of course, the community doesn't quite take it that way. I think the community takes it as, okay, it's important not that I do my research on MNIST-M, but that I show my result on like the 7 data sets in wilds. That's what it means to be good on shift. So then you do this. And then, of course, I end up hearing from my friends working in medical imaging at hospitals say, we took the method that worked on wilds for accuracy estimation, and we apply it on our hospital. And we look at, the change between like radiologic equipment, and all the accuracy estimates are like wildly off. Like it says the accuracy is 20% when it's 80, and it says it's 80 when it's 10, or something like this. So we have this weird problem. I think within the community, we have this kind of paradigm battle of like, should we be making assumptions, or should we be doing something that feels more empirical? And it's very easy because for any kind of method someone comes up via the tinker and look empirically method, it's very easy for the theorist or the theoretically inclined person to say, let me come up with a very straightforward assumption where what you're doing is obviously the wrong thing. And it's very easy, conversely, for the empirical person to take your method that was developed under some assumption and apply it on, CFAR-Q and say, oh, it didn't work. So we have this battle, but meanwhile, while we're duking it out amongst each other, the reality is nobody's using any of it. And so, right. The assumptions that we make to do the research that we feel nice about don't map neatly onto the kind of problems that we're observing. And neither do the data sets we're seeing. No, I'll be surprisingly, I've grown up. I'm better at time management now.
Just maybe 2 questions. One, you said nobody's using any of it. Is that, I know you're not using any of it, but how do you know nobody is using any of it? Like a big company.
It's like, I don't know. How do you know nobody eats cement for dinner? Like, you spend a lot of time around humans, and you've seen a lot of people eat dinner, and you're a
I'm saying
high-performing human.
About every big company, and
sure,
every startup, the type of distribution shift they have, you're saying nothing works, and it's always a human who has to come up with a new solution on the fly. Is that what you're saying? That's the first question.
Yeah,
the second question is, you're exposing a bunch of problems with how research is relevant to the real world. Right?
Sure.
Are there solutions you're going to propose?
Funny you should ask.
Okay.
So maybe like that's maybe the first part of the talk is like maybe observations from academia. Where am I? What am I doing now? So over the last, I don't know, almost 2 years, I've been overseeing technology development at a bridge. And what we're doing is fundamental problem basically is doctors spend about 2 hours doing paperwork for every 1 hour of direct patient care. It's about 50% of all their time is doing scut work in the EHR, 25% of it actually seeing patients, the other 25%, who knows, hopefully lunch is involved. And so the problem we've gone after is developing technology to lighten the clerical burden of practicing medicine. Insight was that a lot of the documentation that they have to complete is stuff that, well, a passive observer, if sitting in the room, would be able to do like 95% of the work for them. So if you had a medical resident sitting in the room, which is often the case, they could basically act as a scribe, sit there, take notes, given all the time in the world, they could draft a decent history of present illness, a problem-based assessment and plan, a social history of past medical history, a family history, medication orders. And then the doctor would still have an obligation, of course, just like, you should check the work of your grad students. They should have obligation to check the work of the scribe and to make any modifications or anything that was in their head that should go in the note that they didn't say out loud to do the work. But most of the work could be done on the basis of just being a fly on the wall and listening to the audio. So what we built is a system that goes all the way from raw audio to drafted clinical documentation. There's a lot of components of this. There's at least just four machine learning models that have to be hit just to get from audio to speech, right? Because you go from raw audio. Great models today have very strong multilingual capabilities, but multilingual capabilities are much better when they actually know what language you're going to speak before you start speaking. Essentially, like on the fly, we have a very fast language recognition model that's recognizing what language is being spoken, which is setting the language token of a speech transcription model, which is then input for an alignment model, a diarization model, being passed through generative pipelines for generating each of the key pieces of after-visit documentation, a set of guardrails addressing known problems. The complete suite of software also involves tools for editing, tools for identifying evidence in the underlying transcript. So oh, where did this come from, or this looks fishy, to be able to highlight it and find where it's evidence in the transcript. And we've deployed the system, we built it, we've been evaluating it, we're continuously improving it, but we've gotten to a level of performance where we're getting adoption across the entire United States. So we went live, I think it was the first like generative AI deployment of healthcare technology in a like enterprise hospital system in April 2023, and we're now deployed at approaching 100 hospital systems across the nation. Tens of thousands of doctors, millions of notes being generated on a like weekly, monthly basis. And all kinds of shifts are happening. So the frequency of different languages being spoken, there's label shift and the language distribution for the language recognition model. There's shift in what accents are being used. Every single time you activate a new hospital system, there's a kind of population shift. The recording conditions are changing. There's changes in overall noise levels as people are recording in different kinds of environments. Or maybe they start recording in the emergency department, whereas previously they had only been ambulatory. There's changes to like what sort of parties are in the room as people become more comfortable. They recognize the multilingual capabilities, start using the recording in visits where maybe caretakers are present, interpreters are present. Maybe there's two people physically in the room and there's one of those blue phones with an interpreter like in via telephony. There's changes in audio pre-processing, right? So as we go from, say, only processing audio captured via our recording app to maybe our recording app on the iPhone to recording apps built into, say, Androids, new phones coming out, web recording, integration into electronic health records mobile apps, such that like we're getting audio passed to us, for example, by Epic. There's shifts among the population of patients as different specialties get different levels of familiarity. There's shifts in like who within those specialties is using the app. So you go from people who are like more early adopter types to people who are more late adopter types who have different patterns of using technology. Being used in new care settings among new customers. There's internationalization on the horizon. There's a lot of shifts that occur just like within the pipeline, like shifts to what inputs to downstream models look like as a result of upgrades to upstream models. So we improve the speech model. Now there's distribution shift in what transcripts look like from the perspective of a summarization model, which induces further like distribution shift in what inputs look like to a guardrail that was trained based on data originally from a previous, before you upgraded the speech model. There are shifts due to training on de-identified data, right? So for research and development purposes, you have to like redact PHI from the raw data, but then you're deploying the stuff in the wilds. There's interesting shifts in behavior. Shifts in behavior as people acclimate to using the product. This is one that's actually maybe kind of benign or even good in the sense that it's a shift specifically driven by a person optimizing the behavior of the model to their purposes. So an interesting one is people don't typically enunciate or like dictate aloud everything they're observing in a physical exam. The doctor's usually like, can you bend your knee? Can you twiddle your elbow? Can you open your mouth? And then they usually don't, when they listen to you breathe, they usually say, sounds good. And then the doctor might start saying like, I don't hear any wheezes, rasps, or ronchi, like your reflexes look normal. So some of those shifts are explicitly like friendly. So it's like what kind of like routines are, and so every company out there who I think is deploying technology that lots of people are using is evolving, and depending on how sensitive the application area is, they may be more or less rigorous or more or less like vigilant, and maybe depending upon the like research or scientific backgrounds of people working there. But like what I like to kind of highlight is that the routine that's emerging around modeling, around deployment and monitoring doesn't look anything like the academic discipline of distribution shift papers. It looks like business processes, right? So I mean, there's a lot of things going on. But first, pre-deployment checklist, evaluation. So maybe the first thing is like something that looks like the standard evaluation. We have evaluation on some set of data that's like representative conversation, some combination of maybe curated conversations, DID production conversations selected at random among those from enterprises with like where this is sort of permitted under like the sort of data use arrangements that we have. Some collection of challenge data sets. This is like one way that already like the distribution shift or shifts over time start getting incorporated is we start building a compendium of like where has the model failed in the past, and every single time you encounter a failure, you have a process for flagging instances that have that failure where a complaint was made, building up a challenge data set, which becomes like a key focus of any future release. So we have, for example, challenge data sets that are constructed specifically to represent multilingual conversations in specific language instances or combinations, or particular noise conditions, or specifically conversations that bring up in discussion, say, new medication names that entered the lexicon after the cutoff date for speech models. We have automated metrics that are used. I won't go into all the, and then we also have a human in the loop judgment, which I think is just 90 seconds. That's pretty good for us. Also, we started more than 5 minutes late. So I'm on to you. Human in the loop judgments, general problem, not about distribution shift, but about generative AI, is that at the end of the day, we don't have great automated metrics that capture all desiderata of interest. You end up, in our case, with running a large number of encounters through both maybe the current end-to-end system, like the status quo, and some candidate system, and actually having clinicians in the loop who are both giving like structured feedback, preference feedback, and sort of putting us in a situation where we're sure that sort of by all standards, as assessed by expert annotators, we're performing better than the status quo system before deploying something. Then we have staged release processes where first we're handing new technology not to like everyone in the wild, but a set of specially trained people who are sort of in frequent contact with our product teams and are giving direct feedback. So how are we dealing with distribution? There's no like magic bullet. Like at the end of the day, it's like a set of a set of product development practices around collecting feedback in real time from actual users, and ultimately making sure you get feedback, have mechanisms to get feedback from end users themselves, from doctors. So we get thousands of pieces of free text written reports from clinicians using our app every single day, who are saying, oh, you missed this medication name. Oh, you mistranscribed that. I would have liked the problems to be arranged in this order, but you arranged them in that order. And these are ultimately both being read, every single piece of feedback, by humans. They're being automatically triaged into categories by machine learning systems that those corresponding encounters form challenge data sets that are part of the evaluation that goes into greenlighting future models. And so we're evolving a whole set of industry practices. It's not just us. Right? It's every single person deploying this technology is evolving a set of practices around how do you deploy technology in a changing world? How do you get feedback? How do you sort of iterate on evaluation in a way that keeps your evaluation practices sort of responsive to the reality on the ground? It just doesn't look anything like the program of research that we imagined when we set out to tackle these problems. It looks more like a collection, like some combination of like traditional evaluation, maybe HCI practices, and like just like business processes around quality control. So, you know, I would just sort of say at a high level, the challenge I like to leave us with is sort of just in general, when we talk about like research on distribution shift, like what the hell is the purpose of this line of inquiry? Is like, are we working backwards from trying to build robust technology? Or are we like kind of like we figured out a way to like we've got a set of technical tools we like to play with, or we've got a particular like puzzle solving domain that we're in dialogue with. But you know, what's not obvious to me is with a lot of these lines of research, both on the empirical side and on the kind of like causal modeling in disguise side, is whether like it's clear to me that we are laying steps along a path. It's not clear to me if that path ever connects back to actually deploying technology responsibly, robustly, usefully in the world. And I think the big challenge for me, like when I think about like what academic work has to say about this broader kind of line of generalization is what, you know, where should we be spending our time? What should we be focusing on? And I'm pretty personally comfortable with saying, hey, we're laying some steps that are, there's a long way to go before we connect to the real world. But this feels to me like a line of inquiry that it's not like the only reason why it's interesting is because of the idea that somewhere down the line, it eventually does connect back to something that's useful for practitioners. And I think the, you know, challenge here is to figure out, well, what is the set of technical challenges that actually get us there? So thank you.
I think we'll take questions to the break.
Just one quick re-announcement. Again, for launch time today, I've seen that a few people have signed up for the launch discussions. Rich, have you signed up?
Of course.
Great. So please sign up for the launch discussions. I'm especially encouraging more senior people to sign up so that it gets everybody going. I signed up last night, so
You are not too late.
So, and then around in the second session, at the end of the second session, I'll just say which launch discussions people have both signed up for, and then decide on, we'll try to decide together on destination restaurants and or local cafes and such. All right, thank you. And so we'll take a break for, we'll come back at 11:30. Thanks.
11:30.